So yeah, so you can decide whether or not you want to turn your camera on since it's
Okay.
recording. Okay. So I don't have anything good, sorry. But I'll get them to you by Wednesday. I try to make sure my grading is done on exams, like 1 week is the max. So I'll try to have them by Wednesday for sure. So I did do the first part, the memory work part, and y'all did really well in that. So I was super impressed. That was not an easy thing. And you memorized a multi-step long proof and you did it really well. So I was proud of you guys, you all. So yeah, so for today, we need to go over the proof of theorem 1.7 and talk a little bit more about primes. And then do the proof of theorem 1.8, which is the fundamental theorem of arithmetic. And that one just has the uniqueness fit in it. So we've got to deal with the uniqueness. And then we'll be done with section 1.3. So so that's kind of cool. I went ahead and posted homework 10, and it has a lot of things like, is 2,375 a prime number or not, and so like if I was trying to look for that, I would probably Google it. Honestly, I mean, you can sit there and try to divide or whatever, but you can also use the Google on that. That's fine, because we don't really have a lot of methods for testing primes aside from plug and chug and do it, so that's all right with me. And then there's one on there where it asks you to write down twin primes. So you can Google like what are the first 200 primes or whatever and find them from that. Okay. So yeah, so let's go through the proof of theorem 1.7. We had talked through it at the end of class last Monday. It's been a week. It's been a week since we talked through this proof. Oh, and none of the printers are working, so I'm going to take roll real quick while I'm looking here. So this is actually Austin's online. Okay, man, where is everybody today? We've got a lot missing. Okay, so yeah, so let's write out theorem 1.7. Oh, there's Brittany. Good morning. So theorem 1.7 says every integer except n, except for 0 and plus or minus 1, is a product of primes. Okay, and for the proof of this, we are going to use the well ordering axiom. Okay, so what are we going to do? Well, So to prove something like this, how do we prove that every integer is a product of primes? Well, the tools that we have so far are to say, assume not, let S be the set of all the numbers that are not written as a product of primes, and then show that we get a contradiction from that. Okay, so that's what we're going to do. So, so one thing we can do here, again, we've defined primes to be positive or negative. So, so here when we're doing this, when we use the well ordering axiom, it has to do with positive numbers, right? Positive integers. And so we're just going to make a quick note here that if we can show that n is a product of primes, then negative n is also a product of primes. So we're really just going to deal with the positive primes so we can use our well ordering axiom. Okay, so let's write that down. So note that if n is a product of primes, let's say n equals P1, P2 up to Pk, then negative n is also a product of primes. So we can say negative n is equal to negative P1, P2, and so on. So we could just change one of those primes to be the negative of the prime, and we get that that is true. So we will only prove for n greater than 0. Because once we have the primes greater than 0, then we can get the negative ones too. So, okay, do I need a better marker? The marker is kind of, I think this glass board is hard to see sometimes. Okay, so let's let S be the set of all integers. That cannot be written as a product of primes. Let's say positive integers. Okay, so the set of all positive integers that are not a product of primes. And we're going to assume by way of contradiction that this is a non-empty set. Okay. Okay. So take a minute and talk with your classmates and figure out what we can say from that. Okay, so we have this set of all integers that are not product of primes. We're going to assume by way of contradiction that that set is non-empty. Where's this going to go? So take a minute to think about that and talk with your classmates, figure out where this is going to lead. We talked through it a week ago, but it's been a while.
And the fact is power, which is the definition of power. But then it's not prime, so. Or like one that is divided or
Okay, so what do we get if we have a non-empty set of positive integers? What do we get? It has the smallest element by the well ordering axiom, right? So it has the smallest element. Yeah. So let's say that here. So S has a small element. Call it, I don't know, we're gonna call it M because that's what they call it in the textbook. So M, so what is M? M is not a product of primes, right? So M is not a product of primes. So M cannot be a prime, right? M is not prime. Does that make sense? Because if M were prime, then it would be counted as a product of primes. And we talked about that, I think, last time, because I think someone had asked, a product prime makes you think that it has to be two unique primes multiplied together. But the way this is written is it includes a number that's prime, right? So M is not prime. Okay, then what? Zach?
I missed it. Why was it not prime?
Yes, because if M were prime, then it could be written as a product of primes, namely one prime multiplied by itself, or like, yeah. Yeah, so this allows, I think here, did we rewrite it on Monday, last Monday? Because I think we said this product of primes thing was a little vague. And so we rewrote this theorem on Monday because we were having this exact conversation. So we could say N equals P1, P2 up through PK for K greater than or equal to 0, right? And PJ and all of the PJs are prime.
I think we said.
One, yeah. Yeah, so we have to have at least one prime there, right? So if M were prime, then I could write it as M equals M, and then that satisfies this idea, okay? So we're allowing this product of prime to be one prime. Okay, so M itself is not prime.
It's the smallest element of it. Only P itself.
Yeah, what do you mean?
So if it's the smallest one, it wouldn't be like, it would be prime.
It would be prime. Yeah, yes. So it's not, so M is not prime. So if it's not prime, then what is it? Composite. So what can we say about M? Yeah, it's that. Well, so if M is not prime, then M is equal to some A times B, right? Where A and B are non-zero, or A and B are greater than 0, right? A and B are greater than 0. And A is less than M, and B is less than, right? So we can break it up into a product of these two numbers that are smaller than M. So what are we going to say about those numbers? That?
If they're smaller than M and M is the smallest element.
That's where we're heading. Yes.
So they're not in the set.
There, what?
They're A and B are contained in the set.
A and B can't be in S, right? So A and B cannot be in the set S, because if they were, that would contradict the smallest element thing. Does that make sense? So A and B are not contained in the set S because M is the smallest element. I think you all are all dancing around the idea here, right? You know, and there are multiple ways probably to write this down. But if they're not in S, then what does that mean? How is S defined? A and B are products of primes because they're not in the set S. The set S was everything that was not a product of primes, right? So A and B can be written as a product of primes. So we can say that A is equal to P1, P2 up through PK, and B is equal to Q1, Q2 up through QS, say, or something like that. But then what? What are we gonna get? That M is a product of primes. Yeah, because M is A times B. Yeah, so M, but then M equals A times B equals P1, P2, PK times P1. So that's a contradiction. And then since we wrote down here that our assumption, our contradiction assumption was that S was not empty, then we have to say, okay, well then that assumption must be wrong. Okay. So S is the empty set. Okay, questions on that? Yeah, William?
Why don't we just say, wouldn't the contradiction be that M was the smallest element?
Well, so
Well, we're saying that then there is no smallest element. Each smallest element we put.
yeah, I mean, yeah, and I think what you're getting at, William, is that there are multiple ways of writing down this contradiction. And so you could have written the contradiction down and said like that, therefore A and B are can't be products of primes, therefore A and B have to be in the set S and M is not the smallest element. So however you want to get there, I mean, I think that would give you also a contradiction that would make that claim false. So yeah. So yeah, I feel like this is a little bit more compelling, but I mean, that's a stylistic question. So. All right, good. Okay, I want to show you all a kind of a maybe this is a nice like historic kind of proof that's really nice. And that is the proof that there are infinitely many primes. Has anyone seen this proof before? William's nodding. Yeah, some of you have seen it. Okay, yeah, this is a cultural lesson right now. This is a nice proof that there are infinitely many primes. And then I wanted to talk a little bit about twin primes, and you may have heard of twin primes before. And then we will encounter our first open problem that you all, it may be the first one you've seen before. Have any of you seen an open problem before in mathematics? One that hasn't yet, some of you have. Okay, so we'll get to an open problem today. So that's kind of where we're heading. I'm gonna move this so that hopefully, Austin, can you see the board decently well?
Yes.
Okay, okay. Yeah, it's weird because I'm doing YouTube and so there's a lag. I don't even know how far behind my video is, but I don't know if you can experience the lag though. Anyway, we'll just keep going. So there are infinitely many primes. So here's how the proof is going to go. So what we're going to do is you would have to prove it by contradiction, right? You don't have any footing in any other way. How can you prove there are infinitely many primes, right? So you assume that. And so then we get this thing where we have finitely many primes. So let's just assume that we have the only primes we have are 2, 3, 4, not 4, gosh dang. 4 is not a prime. 5, 7, and 11. Okay, so let's assume that those are the only primes that we have. Okay, and there are no other primes besides that. So can you, and some of you have seen this before, so you know, can you take what we have here? We have this finite list of primes, and can you construct a number out of this finite list of primes that is not divisible by any of those primes? Okay, so that's your task. So take those 5 primes and use them to construct a number that is not divisible by any of those primes. Okay, so I'm gonna give you a few minutes to think about that. You can talk to your neighbors too, of course. You can talk to your neighbors too, if you wanted to. See what you can come up with. This is.
Sounds, what type you get? What is that?
So like if they're on top of each other, they want.
Yeah.
But yeah,
Okay, did you come up with one?
So it's any number that isn't divisible by any of those.
Yeah, you need to make a number that's not divisible by any of those. Did you get
47.
47? Okay, so how did you construct the 47 out of those?
I mean, by 2s, I was thinking, okay, anything that's even. And then 3s, I was like, okay, 3, 6, 9. 5s, anything generally with like a 5 or a 0 at the end. And then I was looking at 7, and I was like, okay, 49 is like 7. And then I was like, okay, well, you go down 48, that doesn't work, there's 2. And then I was like, 47.
Yeah,
That's
it
the way.
You know, what you're describing there is really similar to something called the sieve of Eratosthenes. Have any of you heard of that? So the sieve of Eratosthenes does kind of exactly like what you were saying. It would take all the numbers and say, okay, I know that even numbers are not, well, I guess 2 is prime, but okay. So 2 is prime, but all multiples of 2 I can cross out because they're not going to be prime. So the sieve of Eratosthenes is a way to generate primes. So it's going to knock out all the multiples of 2 and then knock out all the multiples of 3. 12's gone, 15's gone, and so on. And then knock out all the multiples of the next prime, right? Or then knock out all the multiples of 7 and so on. And what's left will be just primes. Okay, so it's kind of like what you were describing there. Yeah. Okay, other ideas? Yeah.
I added up the first 4 numbers to get 17.
Okay, so 2 plus 3 plus 5 plus 7 equals 17. Okay, and that number is not divisible by any of those numbers. Well, it's prime, so. Yeah. Okay, other thoughts?
I did 11 times 11 and then plus 10 because it will be a factor of 11.
Okay. 11 times 11 plus 10. Okay, and that is not going to be divisible by 11 for sure, right? Is it divisible by any of the others? So this part is not divisible by 7, and that part's not divisible by 7. But when you add them,
I think that's a 131.
131, and did you
It's not
try?
even? Yeah.
You tried dividing everything?
Yeah.
Yeah. Paula?
I was gonna say, I think, yeah, that word we were talking about, I think if you did like 11 times 11 plus, like there's other numbers you could add that it wouldn't work for, so maybe think maybe because 10 is one away from 11.
Okay, yeah, 10 is 1 away from 11, so it's not gonna be divisible by to 11, yeah. If you add 10, it's not gonna be divisible, yeah.
If you add 12, it's divisible by 7.
And two.
But you can get 12 with those numbers, though, could you? I guess if you added another 2.
Yeah, so this idea of being 1 away from a multiple is something that can be useful, I think, when we try to generalize this. Yeah. Well, so in thinking about this, I don't know that I really expected you to come up with the strategy of the proof, but I think these are helpful thoughts, you know, okay, I want to have something that's not a multiple of any of these numbers, right? And I want to be able to prove it, like, for sure, that it's not a multiple of any of these numbers. And so this idea of multiplying them together and getting 1 away is going to give us something that we can generalize. And so consider this number: 2 times 3 times 5 times 7 times 11 plus 1. Will that number be divisible by any of those numbers? Definitely not. It's it's 1 away from a multiple of any of those numbers, right? And so that number, we can say for sure, is not divisible by any of those numbers. And that's going to be the strategy that the proof uses, okay? Is we're going to say, let's take all the finite number of primes that we have, multiply them all together and do +1. And that'll give us a number that is going to be not divisible. That's going to be gigantic. It's going to be a huge number, right? And I don't even know what that number is. Did someone, oh, you said.
2,311.
Yeah, so it's huge. So you're not going to just think of that number off the top of your head, right? But because of the way that number is structured, I can see right away that it's not going to be divisible by like any of those primes, right? Because of the +1 and the things. Okay. And so that's the structure that the proof is going to use. All right, are we ready? So let's prove it. So I need my eraser. Oh. Okay, so we're going to, so here's the theorem. This one is not listed in your textbook, so this is just for extra. I felt like when we were talking about primes, we needed to go over this proof because it's just a cultural thing. So there are infinitely many numbers. There are infinitely many prime numbers. So here's the proof. So assume by way of contradiction that there are finitely many prime numbers. And let's list them out. P1, P2, up through PK. So there they are, all the finitely many prime numbers. And so we want to consider what number? We're going to multiply all those together and add 1. Okay, and so what can we say about M? Well, M is not prime, right? So M is not prime because it's not in my list, right? M is not prime because it's not in my list. Does that make sense? M is not prime. But M is not in the list. Y'all agree that this is a number that's different from any of the numbers here? Yeah, it's gotta be. So if it's not prime, then it must be divisible by one of those primes, right? So M must be divisible by one of the PJs. Or one of the PJs. So let's say if PJ, so let's say PJ divides M. Let's say assume PJ divides M. Then PJ divides M minus P1, P2 up through PK. Since PJ is in that list, right? It divides M and it divides that, so it should divide the difference. But what is that difference? The difference is 1, right? So PJ divides 1. Is that possible? No, because P is a prime. So a prime has to be something that is not equal to plus or minus 1, right? So that's our contradiction. So I'll write it out in words. This is a contradiction. I guess I can show you symbols. So for contradiction, sometimes we use like a hashtag like that, kind of tilted a little bit. Or you can also use these like arrows pointing at each other, that it's a contradiction. So that's another symbol for it. Those are the two I've encountered. There may be others for a contradiction symbol, but
I've seen like it's the same symbol we use for perpendicular in geometry.
oh yeah, like this.
Yeah.
For contradiction. Yeah, so those are some symbol. I guess I've seen that before. Anyway, this is a contradiction. So there are, what was our contradiction assumption? We assume by way of contradiction that there are finitely many, so there are infinitely many primes. And there's the proof. Isn't that cool? It's really elegant. It's a really, really elegant proof. So, so that's a little bit of culture, a little bit of history there of that proof. Okay, and so twin primes are primes that are 2 units apart. So some twin primes are like 3 and 5 are twin primes. 5 and 7 are twin primes. 11 and 13 are twin primes because they're right next to each other, right? So they're within 2 units of one another, are twin primes. And so the twin primes conjecture is that there are infinitely many twin primes, okay? And that's an open problem. So, so mathematicians have not been able to prove yet that there are infinitely many twin primes. We believe it to be true, but it hasn't been formally proved. So, so that's something you can Google sometime, twin primes conjecture. So, so this type of argument is not going to work on the twin primes. I'm proving there are infinitely many twin primes. So that's kind of a cool little thing. So the twin primes conjecture, there are infinitely many twin primes. And on your homework, I'm going to have you write out all of the twin primes that are less than 200. So you can just Google that and write out all the twin primes that are less than 200. You can Google, there are some nice visuals that show like all the numbers written out and like the prime ones are highlighted, you know, so that's kind of nice. So you can find something like that on the internet and write up all the twin primes that are under 200. So yeah, so there's an open problem. It's kind of cool to see something that's so easy to state and yet so hard to prove. And there, if you Google it and you look at the Wikipedia page, there are some really interesting properties of twin primes. And so If you're ever looking for a project or something you wanted to do, like, I don't know, are any of you, OSU teach majors? No, some, yeah. So when you do your, is it, the project-based course that you all do? What is it called?
Research methods.
What is it?
They do research methods.
Research methods. Have you done that already? Yeah. So something like this could be something you could investigate for research methods. Obviously, you're not going to prove it, but but you know, but you could do a poster about it and talk about twin primes and some of their characteristics and things like that. It's just neat to see an open problem, and I think it's really cool to be able to, like, when I was teaching, I taught junior high for a year, and to be able to talk to the kids about, like, here's a math problem that people don't know the answer to, like. And it's just kind of cool for them to be able to see that. So I think a lot of times people think, oh, mathematics is all done. It's all set. It's all over. But it's not. So it's just hard to find a problem that's easy to state, you know, that hasn't been proved. So there's another nice one called the Goldbach conjecture. So if you ever want to Google that, the Goldbach conjecture is another open problem that it deals with prime numbers also. Does anyone know the statement of the Goldbach conjecture? So let me write down open problems dealing with primes. So the twin primes conjecture is that there are infinitely many pairs of twin primes. You know, Colin?
Is Goldbach the one that's like every even number is the sum of two primes?
Yeah. It's every is it every even number or is it every number? Every integer.
It's gotta be every, oh, there's one about 3 primes for odd numbers, but I just
Okay.
remember the even numbers.
So yeah, actually, well, let me Google it real quick. I thought it was every integer, but maybe it's every even integer. So let's see. You're probably right. I haven't Googled it in a while. But if I'm gonna write it up on the board, I want to make sure I've got it right. Okay, Goldbach conjecture. Every even whole number greater than 2 is the sum of 2 prime numbers. So there's the Goldbach conjecture. So that hasn't been proven either. That's another open problem related to primes. So there you go. Anyway, so that's just a little bit of culture and history there. Okay, so let's move on to theorem 1.8. So for theorem 1.8, we just have to do the uniqueness part. So we've already shown that every integer is a product of primes. That was theorem 1.7, we proved that. Now we just need to show the uniqueness bit. And gosh, I was sitting there this morning, I was like, oh, I need to write out that proof, but oh, it's so boring. It's a really boring proof. Anyway, go ahead.
I have a question on the gold block.
Sure. James.
But every even number.
Every even number. I don't know why I said prime. Yeah. Every even, that doesn't make any sense. You're exactly right. Yeah, every even number greater than 2 is the sum of 2 prime numbers. Sorry, I just had prime on the brain, so I kept writing it down. So okay, good. Okay, so yeah, so how do we show uniqueness? We want to show that this prime factorization is unique. What's the strategy for showing uniqueness? Zach?
Suppose that there's another way, and then.
Yeah, so you just suppose, okay, so theorem 1.7 says that I have a prime factorization. So I've got this prime factorization, assume there are 2, right? And then show that they must be equal to one another. So that's essentially what we're gonna do. And so So we'll have to deal with how many, like the length, the number of primes there. So we can have one prime factorization that has k elements and one that has s prime factors. And we'll just have to show that k equals s. And we'll have to show that, you know, each of those factors are unique. So, all right, so let's write it all out. So I apologize that this proof is rather boring, but we got to get it done. So. Okay, so here's theorem 1.8. So this is the fundamental theorem. Okay, so every integer is attached to primes, and this prime factorization is unique. In the following sense. So if n equals P1, P2, PR, and n equals Q1, Q2, QS, then R equal S, and after reordering and relabeling, we have P1 equals plus or minus Q1, P2 equals plus or minus Q2, up through PR equal plus or minus PR. Okay, so I'll let you catch up. And I wanted to write down, we're going to refer to theorem 1.7 and we'll refer to corollary 1.6. So let me write the statements of those two down. So corollary 1.6 says, these are what we're going to refer to here. This is the one with the proof that we didn't like because it had the like continue in this manner kind of thing. And this proof is going to be that way too. Because we haven't done induction yet, but we're going to do induction Wednesday. We'll start induction on Wednesday. And that will allow us to nail things down a little bit better than this continuing in the following, you know, continue in the following manner. So, so this says if P is a prime and P divides